Hello. So 2 days ago we talked about superposition principle and interference of waves. And you might remember I showed you this, this program by Professor Casper that simulates two waves with some phase shift between them, shown in red and blue. And then the sum wave is shown in green. And then as we change the phase difference, we observe the constructive or destructive or partially destructive interference. And we also talked about a wave interfering with its own reflection. And we can simulate that in this program as well by reversing one of those two waves. And now you see that the resulting wave looks like it's not traveling at all. Rather, it just vibrates back and forth. And that's why this green wave is called a standing wave. And that's exactly what happens if a wave reflects off one end and runs back onto itself. We can demonstrate that with a string that is fixed on one side, and then try and excite those vibration patterns. And those vibration patterns are often called vibration modes also. And they are characterized in this case, since it's just in one dimension, by regions which do not move, called nodes, and regions that do move maximally, which are called antinodes. So for example, this is the simplest case, the so-called fundamental mode. We have a node only on the two ends that are fixed and a maximum vibration in the middle of it. So the next highest mode has two of those antinodes with maximum vibration and three nodes altogether, one at each end and one in the middle. And then finally the next one has four nodes and three antinodes, and so on and so on. And of course, always at the ends there must be nodes, since those points are fixed and therefore they cannot vibrate. And each of those modes has a frequency associated with it. Those are called natural or resonant frequencies, just like in the case of forced harmonic motion. The fundamental is also called the first harmonic, and then the higher order modes are called the second, the third, and the fourth harmonic. And those higher order modes are also called overtones. And each one refers to such a pattern. So we can actually look at what is the wavelength and frequency of those standing waves. And we observe that the standing wave, because of the boundary conditions, that is, that it's fixed on those two ends, the wave has to fit inside this box. And because of the way the standing wave looks like, it's actually the first overtone, or the second harmonic, where exactly one wavelength fits in the box. The first one, we only get half a wavelength. And so we sort of have to imagine how the wave would look like outside the area where it's really defined. So if I duplicate this picture here, and we have the fundamental mode here, we imagine that it continues like this. This is the distance L for the rope, and here we have no rope, but of course it would also be the same distance here. And we see that the lambda of the wave, where it repeats itself, is actually 2L. And since this is the fundamental mode, we call this lambda 1. And we can also say this is 2L over 1. If we now look at the overtones, then for the second harmonic, the first of the overtones, we fit exactly 1 lambda inside this box, and we get that lambda 2 equals 2L over 2. And this is actually a general formula. The nth harmonic will have a wavelength that is described by twice the length of the rope divided by the order of the harmonic. So, for example, for the third harmonic, we get 1.5 wavelengths fitting inside that box, or the wavelength is twice the length divided by 3. So let me now calculate an example to make this a bit more practical. So let's assume we have a piano string, and the piano string is 1.1 meters long, and it has a mass of 9 grams. And the question is, how much tension must the string have so that it's vibrating at a fundamental frequency of 131 hertz? And what are the frequencies of the first 4 harmonics? And so the answer is, for the fundamental mode, we know that the wavelength is twice the length of the string. And since the string length is given as 1.1 meters, that means that the wavelength is 2.2 meters. So we found the wavelength of the fundamental mode. We, of course, also know the frequency of the fundamental mode because it's given, it's 131 hertz. And from those two, we can find the wave velocity, because that is, as usual, the product of frequency and wavelength. So if we multiply those two numbers, we get 288 meters per second. We also know the linear mass density, because the mass of the string is given as 9 grams, and the length of the string is given as 1.1 meters. And so we can divide the mass of 0.009 kilograms by the length, or the 1.1 meters, and we get 0.00818 kilograms per meter. And now we can use the equation for the that relates velocity and tension and mass density. So we have the velocity square equals the tension force divided by the mass density, and that means that the tension force must be the mass density times the velocity square. We've already calculated the velocity, so all we have to do is plug in the numbers, and we get that the tension force must be 680 newtons. So now to the B part of the problem, what are the frequencies of the first 4 harmonics? And to do that, we first observed that we had our formula for the wavelengths for the harmonics. We now need to express that in units of frequencies. So we know that the wavelength of the nth harmonic is twice the length of the rope divided by the order of the harmonic. And we know that the product of the wavelength of the nth harmonic times the frequency of the nth harmonic must be equal to v, the velocity of the wave. And therefore, we can solve for the frequency of the nth harmonic. And it's the velocity v divided by the wavelength. And if we plug in this equation here, then we get v divided by 2L multiplied with n. So this is the frequency of the first harmonic, or the fundamental, and this is the order of the harmonic. So all we have to do is we have to multiply the frequency of the fundamental with the order of the harmonic that we want to look at. And the fundamental frequency is already given as 131 Hertz. So that's already one result. And so the next one is just twice as much, or 262 Hertz. The third order is 393 Hertz, and the fourth harmonic is 524 Hertz. So now to the mathematical representation of the standing waves. And we've seen from this demonstration program by Professor Casper that we can think of a standing wave as the sum of a traveling wave moving to the left plus a traveling wave moving to the right. So we therefore say that we have two waves, two sinusoidal waves. One looks like sine kx minus omega t, and one looks like sine kx plus omega t. And we add those two together. And in order to do that, we exploit a trigonometric identity that the sum of sine x plus sine y equals twice the sine of 1/2 of x plus y times the cosine of 1/2 x minus y. It's one of the many trigonometric identities there are. And if we use that on the sum of those two waves, which looks like this, we get twice the amplitude. And then the sum of those two terms inside the sine function divided by 2 is simply kx. So it's sine kx. And the difference of those two arguments of the sine function is just omega t. To show that a little bit more clearly, so we have x equals kx plus omega t, and y equals kx minus omega t. And if I sum those, then I have x plus y equals 2kx. If, however, I subtract them from each other, then I have x minus y equals 2 omega t. In this sum, we actually separate the spatial dependence of the wave from the time dependence. And that's exactly why it looks like it's standing, because this part describes where are the nodes and where are the antinodes. And this just describes the harmonic motion or the vibration of the entire thing. And now we can reformulate that requirement that the standing wave must fit inside the box as that sine of kl equals 0, where k is the wave number. And that means that kl must be equal to pi, 2 pi, 3 pi, 4 pi, and so on. And the antinodes are obtained in between if kl equals pi over 2, 3 pi over 2, 5 pi over 2, and so on. And since we know that k is 2 pi divided by lambda, we can also say this corresponds to x equals lambda over 4, 3 lambda over 4, 5 lambda over 4, and so on. And for the nodes, we recover the formula. So other wave phenomena which were not covered in this class are wave dispersion. In this case, the phase velocity is not a constant, but it depends on the frequency of the wave. And if you remember another demonstration program by Dave Casper, I showed last time, which showed that you can represent basically almost an arbitrary shape by building it up from sine waves with different frequencies, like this, for example, for the sawtooth. If we have such a dispersion where the wave speed is different depending on the frequency, then those shapes don't remain intact. They will change their form as the wave travels. In essence, what it means that pulses are washed out and sort of disappear. And that is why this phenomenon is called dispersion. Then another interesting phenomenon that probably most people could name when they think of waves at all, the breaking of waves. All the waves I've showed you, they never break. And also shock waves, like what happens when a plane goes through the sound barrier. And those are typical behaviors of nonlinear waves, which are much harder to handle. In this case, the phase velocity depends on the amplitude. For example, you can model the breaking of a wave by you have some pulse. And if this part moves faster than this part, then this pulse will sharpen, and eventually it will do this, and then the wave collapses. And in that case, often chaotic motion is the outcome of it. Nonlinear waves appear in many real-life situations, including traffic jams, for example. But they are not part of this class. So let me now summarize the chapter 15 about waves. So first of all, the sources of the waves are vibrating objects. So the vibration of the object doesn't travel, but the excited wave travels outward from the source. Such waves can be single pulses, or they can be continuous, like a sine wave. The wavelength lambda is the distance from wave crest to wave crest, or wave trough to wave trough. So if we have a sine wave, for example, then this one would be a lambda, or this one would be a lambda, or this one would be a lambda, where this is distance x. The frequency is the number of wavelengths or crests passing per unit time. The amplitude is the maximum deviation from equilibrium, or the height from the equilibrium level to the crest or to the trough. The wave velocity is given by the product of the frequency and the wavelength. So there are two kinds of waves, transverse waves and longitudinal waves. And in the transverse wave, the oscillations happen perpendicular to the direction of propagation. And for a longitudinal wave, those oscillations are parallel. Waves transport energy, and we can define an intensity, which is the average power per area. And this intensity is proportional to the square of the amplitude. In the case of three-dimensional waves, this intensity decreases with the square of the distance. Intensity is proportional to 1 over the radius square. The amplitude, however, which is, since intensity is also proportional to amplitude square, the amplitude is proportional to 1 over the distance without the square. So both intensity and amplitude decrease, but one decreases linearly and one decreases with the power of 2. Then we can define a wave number as 2 pi divided by the wavelength. in analogy to the angular frequency, which is 2 pi divided by the period, or 2 pi times the frequency. A sine wave is described by a displacement as a function of position and time, given by this expression, amplitude times sine times of wave number times position, plus or minus angular frequency times time, plus some angle phi. And if it's a plus sign, the wave is traveling to the left, and if it's a minus sign, it's traveling to the right. And we can also re-express that as k times x plus minus vt, where v is the velocity of the wave, since the velocity is omega divided by k. Waves passing through the same region of space at the same time add. That's the principle of superposition. And in this addition, or this interference, it can be constructive, destructive, or partially destructive, depending on the phase difference between the waves. Waves reflect off objects, and in that reflection, the angle of reflection equals the angle of incidence. Waves also change direction when they encounter a boundary with different wave velocity. And in that case, the law of refraction is that the ratio of the sine of the incident and over the sine of the refracted wave equals the ratio of the phase velocity. Finally, waves can do a third thing. They flow around obstacles or diffract. In that they also change direction, and the angle of that direction change is about the wavelength divided by the size of the object. But this is just a rough figure, rough rule of thumb. When waves interfere with their own reflection, then standing waves can be produced, if conditions are right. And these appear as vibrations which appear to stand still. And several such vibration patterns or modes are possible in standing waves. The standing waves occur only at the resonance frequencies of the system, and the lowest of those resonance frequencies is the fundamental. The others are called overtones. They're all sorted and labeled as nth harmonics. The nodes are regions without vibrations, and the antinodes are regions of maximum vibration. And if we have a chord of length L fixed on both sides, then the wavelength of the nth harmonic is given by lambda n equals 2L over n, or the frequency of the nth harmonic is n times the wave velocity divided by twice the length. Then let me move to chapter 16, which applies the theory of waves to something we are fairly familiar with, and that is sound. So first of all, there are sort of two meanings of when we say sound. One meaning is simply a physical sensation that we have when we hear something. So that has something to do with how our ear is built, in addition to the physics of the system. Or we can mean longitudinal pressure waves, which produce this physical sensation. For sound to be heard, we need three things. First, we need a source. Those are vibrating objects. Then we need a medium that transports the energy of that vibration, for example, air. And finally, we need some kind of a detector, for example, our own ears, but we could also use microphones. The wave intensity is related to the sensation of loudness. The wave frequency is related to the sensation of pitch. As far as pitch is concerned, human ears usually have an audible range where we can hear sound between about 20 Hertz up to 20,000 Hertz. And that, of course, varies person by person. And as you grow older, typically the higher end of that audible range tends to become smaller. So older people usually hear only up to about 10,000 Hertz, not 20,000 Hertz. Beyond the audible range, if it's above, we call it ultrasound. And if it's below, we call it infrasound. Let's now talk about the medium. The wave velocity of sound waves in air is roughly 331 meters per second at 0 degrees. And then you correct 0.6 meters per second for every degree above freezing. So for room temperature, about 20 degrees Celsius, for those conditions, the sound speed is about 343 meters per second. So the sound speed depends on other parameters like the temperature. It's also different for different media. Sound can propagate in other media than just air. So, for example, if you replace air with helium gas, then the sound speed basically triples. And it's even faster in hydrogen gas. In general, the sound speed is slower in gases and faster in liquids, and it's the fastest in solids. And you can see that from this little table here. So let me start with the first example. You probably are very familiar with the rule of thumb that helps you estimate how far away a thunderstorm is, simply by observing the time between seeing the flash of lightning and hearing the thunder. And the rule of thumb is that there's a distance to the thunderstorm of 1 mile for every 5 seconds before the thunder is heard. And we can easily explain that with knowing the value of the sound speed. First of all, we note that the light speed is very fast, about 300,000 kilometers per second. And so we can neglect any time elapsing between the lightning happening and us seeing it at a distance. The sound wave produced by the thunder travels in 5 seconds a distance of typically about 1,715 meters, just simply 5 seconds times 343 meters per second. And a mile is 1,609 meters, which is fairly close to 1,715 for rule of thumb at least. And therefore, the thunder sound wave travels about 1 mile every 5 seconds. And therefore, we can estimate what was the distance by observing the time difference between, the apparent time difference between flash and thunder. So sound waves are longitudinal waves, which means that, that the air molecules vibrate along the propagation direction. We can, for example, look at a sine wave for sound. So this has, as usual, an amplitude, then sine of the wave number times x minus the angular frequency times time, where the wave number is 2 pi over lambda and the angular frequency is 2 pi divided by the period. One can also consider it a pressure wave, and that is, it produces a periodic variation of the air pressure. And that can be represented by mathematically in this way. We have some pressure amplitude times cosine kx minus omega t. So to further describe the sound wave in, for example, air, we need an additional dynamic ingredient, and that is the so-called bulk modulus. A bulk modulus describes how compressible volume changes when you apply pressure. So let's say we have some volume V, and we apply some pressure, and it becomes smaller. So now so this one was the volume V, and this one is the volume V minus V plus delta V, where delta V is typically smaller than 0. Then we can relate the ratio of the volume change divided by what the volume was originally to the pressure difference by a constant which is called the bulk modulus. And it's usually denoted with a capital B. So let's now consider a particular type of volume, which is a cylinder of area S and thickness delta X. So if we now apply a pressure on the lids of this cylinder, then the delta X will become slightly smaller by a distance of delta D. And we can then find out how big is this distance by using the bulk modulus. So the pressure change delta P is related to the volume change by the bulk modulus. So delta P equals minus B times the surface area times delta D divided by the surface area times delta X. So delta D is how much delta X changed. We can write symbolically that after canceling out the surface area S, that delta P should be the partial derivative of the volume with respect to I'm sorry, not the volume, the partial derivative of D with respect to X. And if we now plug in the equation that we had for our sine wave, so D equals A times sine kx minus omega t, and we form the derivative with respect to x, then the a is a constant, doesn't change. The sine becomes a cosine, and we pick up an extra factor of k, and this remains kx minus omega t. So if we then multiply with minus b, we get the pressure change as a function of position and time as b, the bulk modulus, times the amplitude, times the wave number, times cosine kx minus omega t. And those expression in parentheses here, this product of bulk modulus, amplitude, and wave number, that we can call the pressure amplitude delta Pm, or delta Pm equals BAK. So what we observe if we do that is that while the original displacement was A times sine kx minus omega t, this pressure difference as a function of space and time is delta Pm, or the pressure amplitude, times the cosine of kx minus omega t. And that means that those two waves have a phase difference between them. So that is indicated in this graph at the bottom here. So if we look at displacement as a function of time, for example, at position 0, we start with 0 displacement, but the pressure difference is actually maximal. It's the lowest pressure we ever get, so the pressure difference to 1 atmosphere is maximal. So there's a 90-degree phase shift between those two descriptions. Both descriptions are equivalent, however. Moreover, if we make use of the phase velocity, which can be expressed as the bulk modulus divided by the volume density rho, and that is, I can motivate that this is very similar to the wave velocity we had on a rope. On the rope, we had wave velocity square was the tension force divided by the linear mass density mu. And in air, for example, we have the velocity square equals this bulk modulus divided by the volume density. So the linear density becomes a volume density, and the tension force is replaced by this bulk modulus. So that plays that same role of sort of keeping the medium taut. We can next look at the at this. When we use this relation v square equals b over rho, we can solve for b. Then we know that the bulk modulus is v squared times rho, and therefore in this relation between pressure amplitude, we get that the pressure amplitude is rho v squared times Ka, and then using v equals omega over k, we replace one of those two velocities that appear here by omega over k, and we get that the pressure amplitude is the volume density times the velocity times the angular frequency times the regular amplitude. Or if you want to express it in terms of regular frequency instead of angular frequency, we have an extra factor of 2 pi. Finally, we can look at the intensity. And we know from the previous chapter that the intensity is given by this expression. And we can now look at that expression, and if we pick up an extra rho times velocity in both the numerator and the denominator, then we get rho v omega a in parentheses square, which is exactly the expression for the pressure amplitude. And so the intensity is not just proportional to the amplitude square, it's also proportional to the pressure amplitude square. So as I said before, the description with pressure is equivalent to the description with displacement. The only difference is that, that while we had this prefactor for the intensity in the case of the displacement amplitude A, we get a different prefactor for the pressure amplitude. So as learned in the previous chapter, the intensity is actually the average power per surface area. That is what intensity means. Loudness, however, is the associated sensation of a typical human being. And a typical human being can pick up a sound wave above an intensity of about 10 to the minus 12 watts per meter square. And that is called the hearing threshold, I0. And we can hear sound waves up to 1 watt per meter square. So 12 orders of magnitude bigger than this threshold. We can hear it even beyond that, but then it starts to become painful. Even so, there's a fairly large range where sound can comfortably be perceived by human beings, a factor of 10 to the 12. And as it happens, our sensation of loudness is not so much proportional to the intensity, but it's proportional to the logarithm of the intensity. We therefore define a so-called loudness or sound level. And to do that, Bell invented a general logarithmic unit for ratios, and it's called 1 Bell. And 1 bell means basically a factor of 10. So 1 decibel means 1/10 of a bell, or 10 decibels equals a factor of 10. Mathematically, that means that we take the logarithm of an intensity, compare it to some reference intensity, I0, and then multiply by 10 decibels, and that gives us the sound level. And for convenience, we pick for this reference value the human hearing threshold, I0. So as it happens, the human ear sensitivity depends on the frequency. So we can also define a loudness level, and the unit of that is different. It's called phone. And what it means is the same amount of decibels as if the frequency had been 1,000 hertz. So here are typical curves for the perceived loudness. For example, here 20 phone as a function of frequency. So if we have this kind of intensity here, the absolute sound level of, say, 60 decibels at this frequency, then it appears to us, when we listen to it, about as loud as 20 decibels at 1,000 hertz, and therefore we say the loudness is 20 phone. So I will illustrate that with examples in the next lecture.